You're not going to want to miss this episode of the AI Show where we have Andreas Müller, or Andy, because now we're BFFs, talk about Scikit-Learn, machine learning, and he's got a cool new project up his sleeve. You're not going to want to miss it. Make sure you tune in. Hello and welcome to the special edition of the AI Show where we've got a special guest, Andreas Müller. He said I could call him Andy, so now we're actually BFFs. How you doing, my friend?
I'm great. How are you doing?
Fantastic. So tell us who you are and what you do.
So, I recently joined Microsoft like 2 months ago as Principal Research SDE, I think is the official name. It's a bit long. I've worked a lot on like software for machine learning, in particular on Scikit-Learn. So I've been a core developer on that project for a while now. I also have some other projects like Dabl, and I have a book on machine learning, Introduction to Machine Learning with Python. And so I'm trying to make it easier for people to use machine learning in Python mostly.
So let's start all the way at the beginning, if you don't mind. I'd love to get a sense for how you got into machine learning, how you started getting into some of the projects that you were doing, and what the overall goal is for people. Because personally, I love Scikit-Learn. I feel like we talk about deep learning a lot in the field, but I'd love to get a sense for what Scikit-Learn is and why it's important. So let's start with all of those things. There's so many because I have so many questions for you. How'd you get started?
All right. So how did I get started? So my background is actually in like pure math, and but then after I graduated with about like a master's degree, I was like, okay, so what am I going to do next? And then I saw an article about some people in the same town doing robot soccer, and I was like, oh my God, robots, they seem really cool. And so I started my PhD in that group, but I ended up not working on robots, but actually ended up working on machine learning, first some deep learning, and then some computer vision, structure prediction, and so on. And so during that time in my PhD, I started contributing to open source. I started playing around with Scikit-Learn, and then became a contributor there.
So how does one become a contributor to a project like that, like Scikit-Learn?
I mean, back then it was quite a bit smaller and less popular, I guess, and there was a smaller community. But generally, now, as then you start becoming a developer by contributing. Like it's on GitHub, like any other community open source project, you can just start like making pull requests. My first pull requests were fixing typos in the documentation or clarifying things in the documentation. And so even small stuff is really appreciated. Actually, often small stuff is much easier to get into a project than like huge new things. And so just start contributing, start small, and then engage in a conversation with the project to like where things are going.
So for those that are new to machine learning or are super excited to get started, can you frame for us like what's the difference between the goals of something like a Scikit-Learn versus a thing like a PyTorch or a TensorFlow? Are they the same kind of thing? How are they different? What do you say?
So I think there's two main differences. So Scikit-Learn is maybe a little bit more comparable to, in the deep learning space, fast AI or maybe Keras, which is more like batteries included. So Scikit-Learn really gives you full algorithms and tools to train the models, to validate the models, and so on. Whereas PyTorch and TensorFlow are both much more low level, so they allow you to really tweak what kind of model you're using. They give you a lot of flexibility, but also they require you to do a lot of work. Whereas Scikit-Learn really has like a fixed toolbox of models, and you can pick which model you want from this toolbox, and you have to do very little work to use them, but there's also like a limited amount of customization. And then the other sort of maybe more obvious thing is the domain, which is TensorFlow, PyTorch, FastAI. They're all for deep learning, where Scikit-Learn is what is now called traditional machine learning, which is actually newer than deep learning.
So tell me about that, because tell me about how a traditional machine learning is newer. Look, I went to grad school when SVMs were all the rage, and I'm like you, I'm a math wonk, and I just loved how SVMs have like this perfect mathematical structure and optimization. And I always gravitated toward those algorithms. Tell us about that.
That's actually also what I did during my PhD. So my advisor actually was like super gung-ho about neural networks. That was before ImageNet happened. And I was like, no, this is not working. And then I was like much more going to the optimization direction. But turns out actually like neural networks were just on the cusp of becoming much more important. But so a lot of the technology is from the 90s, right? The math is like mostly from the 90s. There's been a couple of very important innovations like different learning strategies and like residual networks and so on, and obviously transformers now. But a lot of the stuff that people use in deep learning is very similar to what Jan LeCun has in his 1989 paper. Whereas in 1989, random forests did not exist at all.
No, they didn't.
And so random forests have like, yeah, they're, oh my God, I don't want to misquote the year, so I'd rather not. But they're newer than convolutional neural networks by like quite a bit.
And it feels like as we look at what's actually the cool things in machine learning, people tend to gravitate towards deep learning. Do you think we've over-indexed on that side of the house as opposed to some of the other things in Scikit-Learn or the newer machine learning approaches that are not deep learning? Do you think we've over-indexed?
It depends a lot on what your application is and what your goal is. So in terms of research, there's so much really, really amazing research going on in deep learning. Whereas instead of the traditional stuff, the innovations that are relevant for practice are relatively small. So people love gradient boosting. People have loved gradient boosting for the last, I don't know, 5 to 10 years. And this is really like the thing that people really go to. And whereas in deep learning, you have like some like major innovations every year happening that are important innovations. So in terms of research, I think it makes a lot of sense. In terms of applications, it depends a lot on two things. A is what's your trade-off between the work you put in and the accuracy? So and the second thing is what is your modality? Let me maybe talk about the second thing first. So if you're working on image data, video data, sound data, you need to do deep learning. There's like there's no point in not doing deep learning. Probably, did I say text data? Text data probably these days, it depends a little bit, but mostly you also want to do deep learning. If you have tabular data or potentially text data, then actually traditional stuff often fares a little bit better, but that might also change. But here, really the trade-off is the work you have to put in versus the accuracy. So I worked for a while at Amazon, and even at like a company that we perceive as like a very high-tech company, there were a lot of places where they could use machine learning and where they didn't. And so really the big improvement comes from going from a manual process to a principled, like data-driven, potentially machine learning process. And so the hard work is going from zero to that, or from manual to that. And you can do that with logistic regression. And if it's really, really important for you to get like the best possible results, you can then like do more and more complex models, and maybe deep learning, even on tabular data, will give you a bit more performance, but you'll have to spend a lot of time on that. And I would argue that in many contexts, it might be better for you to sort of move on to the next place where your company is still at zero and go from 0 to 90% accuracy instead of going from 90 to 95.
I see.
And so there's some applications where obviously, like if you're doing ad click prediction for Google, like every smallest percentage point is like millions of dollars. So clearly you want to really optimize everything out of it. But I think these applications are actually quite rare.
So what I'm hearing from you, and this is an interesting take, and one that I agree with, is you're saying instead of trying to shave like percentage off of the error like a tiny bit, do something that moves your business forward in a significant way without shaving a little bit. Now, and this is the question I have for you, because look, I was trained as a machine learning person. I went to school at the University of Utah, and I'm familiar with the math and the models and such, but I don't have the horse sense of a data scientist that goes out and looks at a problem. So when you're advising people with machine learning problems, is there a specific path that you give them? Like, oh, my horse sense tell you gave us a little bit of that with like, hey, if it's a table, you should probably not do deep learning. What's the path that you follow for solving machine learning problems? Like, obviously, you're not going to try everything at once, but what's your path? Does that make sense?
Yeah. And so the thing that I start with in all my sort of both my lecture series and all the workshops I give is that you should really start with thinking about your objective. What is your overall business objective? Then how can you measure this? And or what is a good measure for this? And then collecting data to measure it. So I think before you start thinking about doing machine learning, you should think about, let's say I do the perfect algorithm to solve this problem. What will the actual business impact be, and how can I measure this? And then I start from a very simple baseline, like if I always give answer 1, or if I use this very simple if, how far can I get to the maximum business impact that I can get? And so this is actually like all of the things I just said are really, really hard problems, because very often the problem you currently trying to solve doesn't necessarily directly translate to your business objective. Like I know, like several years ago, Spotify used Scikit-Learn to make their artist radio. Spotify as a company obviously wants to maximize subscription because that's how they get money. But how do you relate that to what songs you recommend in the artist radio? Like this is a super indirect thing. And this is the same in most applications. And so you have to have a proxy metric that say like, well, how long did they listen to this playlist or something? But then you need to think about, how does the proxy that I found relate to my overarching goal? And do I have the data to measure that proxy?
So if I'm understanding you right, and I think, let me see if, because the baseline I think is super important. You say start with a business objective, number 1. Find a baseline thing like ran.next less than 0.5, right? Or something,
Yeah.
right? If I were to just use a column in my database to predict, and then what you do is you find a proxy measurement or a measurement that maximizes whatever your objective is. And sometimes you can't find that, so you find a proxy, and then you use the baseline together with the proxy to see if the machine learning algorithms you're using are actually helping you for the. Did I get that right?
Yes, I think so.
And so the question that I have for you following this is, how has Scikit-Learn evolved to help with these kinds of problems?
So Scikit-Learn comes from a much more sort of scientific perspective, and so it really focuses on the modeling aspect and not on the workflow that's all around this. And I think it's very hard to try to solve many of these problems with software because they're not software problems, they're business problems. And as programmers, we always like to have technical tools, and often that's not the right solution. What Scikit-Learn does is, let's say, oh, I have the data, I want to use machine learning, I know what the effect of this is going to be on my overall process. Now I want to use logistic regression. Okay, it's 3 lines in Python. I want to use random forest. Oh, I changed this 1 line and then I have random forest. Oh, I changed this 1 line again and have gradient boosting. And then here's this code to plot all the metrics that are relevant for this.
And I think that's cool because I know that I saw at the beginning, you're like, well, Scikit-Learn isn't designed to actually solve the hard problem, but the way you describe the code is it lets you experiment quickly against the baseline to show whether or not you're actually driving change. And that's the thing I like about Scikit-Learn, specifically how it treats models and how it treats optimization. And it kind of treats them in a uniform way across models. And maybe that's just my limited thinking of it. What do you think about? Is there a philosophy with how you present models and optimization in Scikit-Learn that's important?
First, I want to do a comment that's slightly tangential, which is exactly the thing that you said. Like having nice tooling helps you iterate on the overall process. This is my pitch for my new project, Dabl, which is trying to make it even easier, and just allows you to focus really on the big picture. That was the idea of Dabl. Wait, so what was your question?
So the question is there a general philosophy? Now that you've introduced Dabl, we're not going to leave that, but I'm going to leave that for a little bit later. So the question I have is there a general philosophy with Scikit-Learn? Because some of the models that are in there are radically different in terms of shape, like an SVM and a decision tree. They're not the same things at all, but it feels like they're treated in a similar way. Is there an underlying philosophy with Scikit-Learn that lets you do this kind of approach?
I mean, if you ask me, I would say that our interface is actually super inconsistent in some ways. So, which is mostly for historical reasons. Like we have a lot of users right now, so changing anything is super hard. And so, I mean, the underlying philosophies is like make things easy for the user. Think about what is the code the user has to write to use this, and use as few concepts as possible. Whenever a programmer introduces a concept, he has to explain the concept, or she has to explain the concept to the user, and that's the hardest part in programming, is having the user understand all the constructs you had in your head. And so we try to have not too many of those.
I see. But is there a philosophy? Like, look, for me personally, the thing I've liked about Scikit-Learn in general is that for me, a model, because look, I was a programmer for like a decade and then I went to grad school. And so I think of models as functions that we don't write. We just lazily write with data. And so the way that you separate all the models out and you show what they are, and this concept of fitting data to it, to me is super interesting. Are those same concepts the same across all of the models? Obviously, there's differences between them.
Oh, yeah. I mean, the API is completely consistent across all of the models. And yeah, basically, I recently had a paper rejected about how you can frame these concepts, which is there's basically two ways to think about it. One is you have a stateful object that consumes the data and then changes the internal state. If I rewrite Scikit-Learn now, I might use a different concept, which is that you create a stateless object that does a prediction. And so you have one function that creates an object, and this object is a prediction object. Because actually, if you look at applications, in a deployment setting, you usually care about shipping the prediction function. And so Scikit-Learn marries the training and the prediction very closely together, which is very nice from a like teaching perspective and from like I have everything in my notebook perspective. But actually from a deployment infrastructure perspective, it's a little bit annoying.
That's cool, because I wrote a machine learning library in C# when I was a C# programmer, and I had the concept of an iTrainer and an iModel, which are interfaces. Because the reality of the matter is that the true business value of these things is putting these models out into production. Does Scikit-Learn have a facility to do that? I know there's a lot of pickling going on. How does that work with Scikit-Learn?
Yeah, so basically you can use joblib or pickle. That will always work, but has the two caveats that basically you need to have a container with exactly the same version of everything, which is not that nice. The other version is using Onyx. Onyx, I'm not sure like if everybody's familiar with it. It's like a serialization format that Microsoft and NVIDIA and a couple of other companies are working on that basically allows you to serialize arbitrary machine learning models and then run them in like a series of runtimes. And there's a Microsoft Scikit-Learn converter for Onyx, so you can take the model and convert it to Onyx. And Onyx only encapsulates the prediction function. So Onyx doesn't know about training models. Onyx says, given data, this is how you make a prediction with this blob. But this blob is now completely self-contained, and which a pickle file is not.
And that's interesting. I had not heard, because I thought of Onyx as like the PDF for machine learning inference, right? But I didn't know it extended to models such as those in Scikit-Learn. Is this a new thing? How long has this been out?
Ooh, I think it's at least a year or something since the Scikit-Learn converters have been launched. I think maybe a bit longer. I'm not sure like how intensively they're used right now, but it's the best solution that is not pickles, and the best solution that is like platform agnostic and like version independent. So Onyx was originally made more for like deep learning models, but they can certainly also now support random forests and things like this. And I think it's pretty feature complete in that it can support most of Scikit-Learn, I think.
That's cool. I hadn't heard of that. I'm excited to look into it. Now, before we get into Dabl, do you have anything to show us to give people a sense for if they've never seen Scikit-Learn, how it works and how one would go about building something?
Oh yeah, sure, totally. And it's even better. I can do this, and then I live code all of the same stuff in Dabl in a single line.
Ooh, okay. So let's do the Scikit-Learn thing first, and then we'll come back, and then we'll talk about Dabl, and then we'll come back and see how it's better. Let's do that.
Okay, so what you see here is a Jupyter notebook that's running on Azure Machine Learning. So you could just run the same notebook locally in your Jupyter or Jupyter Lab. But here I'm just running it on Azure Machine Learning on a remote compute instance. And so I'm going to use Scikit-Learn here to do a simple binary classification problem. And I start by loading the data. I'm using pandas here to read a CSV file. And this is sort of a classical machine learning data set, which is the adult census data set, which has census data from around 1990 and some of the census properties of people. And the goal is to predict whether their income will be less than 50K a year or more. So Scikit-Learn usually separates the features or say independent variables from the target into two different pandas data frames or NumPy arrays. So here, income will be the target column, and data features will be all the other columns, which will be the input features. So then I'm actually going to do the sort of slightly more advanced Scikit-Learn way of doing it, which is using pipelines and column transformers. These allow you to encapsulate all of your machine learning workflow in a single Python object, which you could then like pickle and store or send somewhere. And so here, I start off by splitting my data into training and test set to build and evaluate the model. The column transformer here is something that allows you to apply different transformations to different parts of your data set. And so I will apply one hot encoder to the categorical variables and a standard scalar to continuous variables. And the way I'm selecting these is as make a column selector that selects the D-type object and make a column selector that selects everything but the D-type object. And so the D-type object are going to be interpreted as categorical, and the rest are going to be interpreted as continuous. This is my pre-processing, and then I pipeline this together with the logistic regression model. So this is a simple binary classification model here. So this basically declares the model. There's another thing I wanted to briefly show. So this is sort of a text representation of the model. A thing that we recently built in. If you set this sklearn.setConfig to diagram, is you get some nice HTML representation that shows you the model. You can click on the parameters and so on.
That's cool.
So that's kind of new. So I want to show this off. Then whenever you have a model, usually you want to tune parameters. And so logistic regression is penalized in Scikit-Learn. So here I'm defining a parameter space for logistic regression to tune the regularization parameter, and then I run grid search. And so this is where actual fitting will take place. It will run cross-validation, and for each possible value of the regularization parameter as specified here. And then in the end, it will evaluate the best model it found on the test set.
I see. So you're actually running multiple models using the parameterization for regularization there.
Yeah.
Okay. Okay. And what is that parameter that the hyperparameter that you're putting in?
C, that's the L2 regularization. So that's, yeah.
That's cool. And then it just goes ahead and goes through all of those things and finds the best model with that regularization parameter.
Yeah. So it does. So right now I'm fitting. So there's 6 parameter. Wait. There are 7 parameters. For each of them, it does 5-fold cross-validation. So that's 35 models. Then it finds, so it trains 35 models for that, and then it finds the best parameter using cross-validation, and then it retrains the model on the full training data set. So in total, we trained 36 models, and then evaluated the last model on the test set.
That's cool. So all of that in just like, I think it's seven different cells, basically.
Yeah.
That's
and this
cool.
is sort of, I mean, this is a relatively sophisticated example where I show off all like the different parts and how you can ideally put them together. You can obviously also just like instantiate logistic regression, call fit, and call score. And then you fit your single model on your preprocessed data or something.
I see. That's cool. So tell me about Dabl for a second. You mentioned a little bit about Dabl. I'm interested in, because I hadn't heard that before, but it's something you're working on.
Obviously, I love Scikit-Learn, but the thing is that Scikit-Learn is really asks you to be very, very explicit about things. So, for example, for the pre-processing we had up here, you say, well, I want to scale my data, I want to hot encode my data, and if I had missing values, I would need to specify how to impute them, and then I have to say specifically, these are the parameters I want to tune, and this is how I want to tune them. And so Scikit-Learn is not opinionated at all. Scikit-Learn requires you to be really, really precise in what you're doing, which is great for some settings. Like in a production setting, you want to be precise in what you're doing. You want to make sure you understand exactly what your model is doing. But maybe if you want to iterate quickly, or you maybe, there's a default that often works, it might be nice to have something that's a bit more opinionated that can give you some results quickly and allows you to iterate really quickly. And so Dabl basically just wraps Scikit-Learn and does most of the cells in this by automatically. And so there's a couple of things in Dabl, but if I want to do what I just did above, then it would be something like, okay, so basically what this does is, so there's basically 3 things or 4 things in Dabl. This is the simple classifier, basically detects what the data types are, does the scale, automatically detects what to scale, and if there's an index that it should drop, and you can also give it a data frame and say this is the target column, and then it does all the scaling and everything automatically, and then it does cross-validation. It runs a bunch of the simple classifiers, like you can see here: dummy classifier, Gaussian naive-Bayes, multinomial decision tree, logistic regression with different organization variants. And so now we have basically here's the same result that we had overall had above.
Interesting.
Only that I only had to write a single line. Well, I used the train split from above, so okay, it's 2 lines. So there's another thing it can do, which is plotting, which I probably should have done before. It doesn't work that well on this. Well, it kind of works reasonably well on this data set. And so it gives you a visual summary. In machine learning, we often have very high-dimensional data sets. And so there's actually no plotting library that's really targeted as doing visualization for machine learning. So here it starts like it gives you a distribution of the target. Then it gives you, there's like 2 continuous variables, age and capital gain. And it gives you like a pair plot for this, gives you a PCA plot, gives you a linear discriminant. And then for categorical variables, it gives you like a mosaic plot that shows you, I'm sorry, I don't know how to deal with this help that's popping up.
Escape, there you go.
Yeah. Says, well, relationship status was actually the most important, and so and it shows for the categorical variables in this mosaic plot both what like the most common relationships are, but then also the class balance in each of them.
That's really cool, and all with a couple of lines.
Yeah, I mean this was 1 line also again, and you can do this for regression as well. And so it does some type inference, and then it tries to figure out what are the most interesting plots to show you. And then so to give you a very, very quick idea of what's happening in your data. And then there's like...
This is all really cool, and I'm excited. You were saying, and then there's more stuff. Like there's more. That's cool.
Yeah, there's 2 more things that are much like these 2 things work reasonably well, I think. There's 2 more things that are more experimental. Like all of this is experimental, but that are even more experimental. And that's basically... One is there's a thing called any classifier, which does like some fancy optimization between all different models, and so it tries out different gradient boosting, random forest, support vector machine, and uses like successive halving and a fixed portfolio, and does like some things that should give you like the simplest version of AutoML, but it should work reasonably well. And then there's another one which is, and it also again does all the pre-processing for you. And then the last thing is there's an explained function that is there to give you all the metrics and interpretation of your model. So it gives you like feature importances and ROC curves and all of this kind of stuff.
So this is all super cool. And I just have like a couple more questions just to finish up, because I know I've taken a lot of your time. So the first question I have, and I think you've kind of pointed it out a little bit, where do you see machine learning going from here? And it looks like a lot of those opinions were influenced what went into Dabl.
Yes, definitely. I mean, so I was thinking about what is the next best tool that I can build that will help people, and so that is sort of was my motivation for Dabl. The other part, so this Dabl is really for like the data scientist, dabbling with the data, playing around, iterating quickly. The other part that I think is going to be important is like more interpretability, also potentially looking at fairness and other ethical concerns, and having infrastructure for machine learning, so that you can have like an experiment repository and like a unified way to access data. So I think some of the big companies have I noticed at least Facebook and Google, they have like centralized ways to do experiments, to do machine learning experiments or other data-driven experiments where people can go in and launch their own trials. And this really gives them a big advantage. But this is not something that like most companies do. And so really doing this right is probably one of the next things. And there's like a bunch of things like Azure Machine Learning has some tools to solve this problem. Databricks has some tools to solve this problem. There's like Kubeflow, and there's like a bunch of other things. But this is sort of a space where I think we'll see a lot of interesting things happening for machine learning now. Just as I said, like the going from zero to something is the hardest part, and I think making this part easier from the infrastructure side is going to be an important piece.
Well, this has been amazing. Where can people go to find out more about Scikit-Learn and Dabl?
Well, dabl.github.io for Dabl. You can obviously find me on Twitter as like Andreas Müller ML. The Scikit-Learn website has like so much documentation, so definitely check that out. If you want, you can also find my lecture series that I did at Columbia on applied machine learning on YouTube. That's so if you know youtube.com/Andreas Müller or something, you can probably find it. And that's like a semester-long lecture that goes over Scikit-Learn and Keras and some other stuff.
Well, this has been amazing. Thank you so much for spending some time with us, Andreas, Andy, because now we're BFFs forever. And again, thank you for watching. It's been glorious spending some time with you. Hopefully you've learned a lot. I know I have. Thank you so much for watching, and we'll see you next time. Take care.